So, hello everybody. I know some of you. My name's Mike Piscopo. This year I'm here with the Deep Sig team. But those of you who don't know me and are involved with GNU Radio, you might see the GoStop14 moniker around. That's all of my stuff. It was originally an attempt when I started releasing things to, if people didn't like it, they wouldn't know who I was. And now I'm up here doing presentations. So I guess the gig is kind of up, right? But so the last couple of years, as Derek mentioned, we've been doing a lot of great work with the Allen Telescope Array, and I love, Derek describes it as unobtainium. Like most of us who do GNU radio work and don't have access to some of this stuff for our day job, like I live in a townhouse community. There's absolutely no way my association would let me put a 6-meter dish out front. Like we just don't have access to it, right? And so there's been this community partnership with the Allen Telescope Array that both sides get the benefit from the partnership, where we've got access to the dishes at the array, and they've got access to all the talent in the GNU radio community. So a lot of this started back in 2019, where about 30 of us, I guess, descended upon Hat Creek Observatory for the first GNU radio hackathon event there. And then that grew. Obviously, we tried to do it again the next year, and COVID kind of got in the way. So there was a virtual hackathon event in 2020. But for those of you that haven't heard about the Allen Telescope Array, there's 42 6-meter dishes that are there. The new feeds cover 1 gigahertz to 11 gigahertz, really wide instantaneous bandwidth. They do a lot of radio astronomy research and SETI research there. But on the weekends now, after the 2020 hackathon, for those of you that are interested in some of the SATCOM, and Daniel Estevez has been involved with a lot of things there too. The GNU radio community has access to 4 of the dishes that are connected to USERP N-series boxes there. So if, like me, you can't have a 6-meter dish at your house and you're interested in doing some science work, SATCOM or radio astronomy, I'd say get with Steve Croft or Derek. And if you're interested in getting access to some of that, I'm sure they can help you out. But I had written the original blocks back at the 29 hackathon to take the data from their correlator and pull it into GNU Radio. And they've been, like everybody else, progress keeps marching forward. So they've been upgrading a lot of their systems. All of that work from what was the old hardware, obviously none of that worked with the new hardware. So one of the things that I said sounded like a worthy challenge for the 2020 piece was to take on upgrading the blocks that we use in GNU Radio that interface with the Allen Telescope Array, so that we can keep processing with that. But the other thing that happened with that was when they did the upgrades and they got new hardware that pulled the data from the antennas, they lost the correlator. And I went, oh, well, now that becomes a really worthy challenge. I've never written a correlator before, but it sounded really interesting, right? I mean, that's the next step to kind of getting these cool sky images that everybody wants to see. So that got added onto the mix. But for the telescope array, the goal with the upgrades is that they're shooting to get 21 antennas on the new feeds this year and eventually get all 42 upgraded. But the interesting thing about it is that there's some really cool use cases there. Like it may not be the biggest array, but it's highly configurable, which means, depending on what you want to do, you can do an awful lot with it. So some of the use cases that we've got are, can you take anywhere from 2, 3, 4, 8, all the way up to 42 antennas? How many do you want to work with to do observations? Could you run multiple pods of antennas at the same time? How do you handle all the correlation out the backside? Could you have multiple correlators running on different boxes, or they're dual CPU boxes with NUMA? Could you run multiple correlators on a single box? And then piggybacking science becomes kind of interesting in that if you're doing some primary correlating work and you want to do something else with the data coming out on the network can be UDP multicast, and then you can run multiple science observations. So there's a lot of opportunity there to do some really cool things. And so part of this evolution that's driving some of the new hardware came about from, I think, a paper back in 2013. Somebody, grad student thesis, did this analysis and determined that taking the FFT and PFB functions and doing those in FPGAs, but then taking all the cross correlation and taking that over to GPUs was a more effective way to do these FX correlators. And so that's what's driving a lot of the new hardware upgrades. So there's the hardware that's closest to the antennas that pulls the data from it are what they call these snap boards. And they can do 2.5 gigahertz of instantaneous dual polarization data captures in this F mode for the correlator. It breaks things down into 44,096 channels, but 2048 of them can be passed on to do other work with. Right now, they're using just over a gigahertz of bandwidth, so they can change how much of that they get. But with the PFBs, it's about 250 kilohertz per channel once it's been channelized. It comes out of the box as 4-bit IQ packed into these single 8 bits, but it's dual polarization. And then it blocks it down into these 256 per channel packets, so it can get it across the network just based on packet sizes. But some of the other things that are interesting there, like they're upgrading to a 100 gigabit network. I don't have a 100 gigabit network at home, right? So a gigahertz of instantaneous bandwidth, 100 gig networks, NVIDIA 3090 cards. And I'll tell you, I've been trying to get a 3000 series card from NVIDIA for like the last year, since last Christmas, and you just can't like get them, right? But these guys have them up there. So there's some amazing hardware that we've got access to do some really cool things. So picture's worth 1,000 words. This kind of summarizes what they call this FX correlator pipeline. Starting out with the dishes, coming through these snap boards. It does all the F engine pieces, comes out across the network on these UDP packets. And then ultimately the correlator boxes will have dual 100 gigabit cards in them to do all the correlations and then writing them out to really high speed NVMe disks. But it's a lot of data. Like just one of the 256 channel packets from one antenna is about a gigabit a second. So if you kind of do the math and scale that out and go, well, if I wanted to do all 2048 channels across all 42 antennas, that's over 300 gig of data per second that needs to be processed in real time. Like that's a lot. So yeah, looking at the goal for this year, if you get it down to about one block of 256 channels, which is about 64 megahertz of bandwidth across all the 21 antennas when they come online, it's about 21 gigs of data. So that sounds a little bit more reasonable as sort of a next step. We've done live observations, and I'll show you some of that as we get through the deck. But we were able to actually, with the new code that's up there, to do 12 antennas in real time and produce sky images, which is really cool. Ultimately, at the end of the day, like the math is great, but I want pictures. And it wasn't just me. Will Farah, who's one of the astronomers on site at the observatory, and Daniel Estevez, the three of us spent an awful lot of time. Will was handling all the real radio astronomy side of it, and I was handling these pieces. And Daniel, we needed another set of hands to help out with all the post-processing, and Daniel really did a great job with that. So, cutting off a little bit. So these are the blocks. These are all out there in out-of-tree modules. There's an out-of-tree module called GRATA, and there's a number of capabilities in there, everything from controlling the dishes and pointing them to these new blocks. The snap source block is the one that actually takes the data from the antennas that are there and pulls that into GNU Radio. And just reminder, they are FFT'd and PFB'd as they come out. So there's a couple different modes that these blocks will work in. They'll take UDP input. We can handle the multicasts. One of the things I did early on to do like repeatable gold data testing was like we could do PCAP captures and actually play that back. So if you wanted to pull that down and not actually work at the array, we could do some testing with that. But this block handles things like the 4-bit output. And if you want to do other things, so like you don't have to go to a correlator. One of the things I always kept in the back of my mind with GNU Radio was I wanted these things to be flexible. Like I didn't want the correlator scenario to be the only one the GNU Radio community could do with these dishes, right? So this block can be put in 8-bit output mode, and you can do whatever you want in a normal flow graph with that. The other one that's over in GRATA, and this is really, I didn't realize how precise some of the timing needed to be in terms of timestamps and such until I got involved with these guys. But synchronizing multiple antennas and making sure that the timestamps stay aligned. If they don't stay aligned, you basically get garbage data out the other side. So there's the synchronizer block. And I kind of highlight this version 3 thing. I can't tell you how many nights or weekends I refactored all of this code trying to get better performance out of it. And the synchronizer block was like the thorn in my side. Like it was one of the original bottlenecks that really was keeping me from getting to more and more and more antennas. It wasn't even the correlator. But it's in there now if there's other science going on. Eventually, that function got moved into the X engine itself. But if you don't want to do X engine stuff and you still want to work with the antenna streams, this synchronizer blocks up in GRATA as well. And then the last one is the actual X engine block. And I already had GRCL enabled, so there was already sort of a foundation for GPU blocks. And this just seemed like a really good spot to put that up there. And I'm not going to talk about it in this presentation, but if anybody's interested in other kinds of correlations and beamforming and stuff, there were a couple other blocks I did along the way for some more traditional stuff that's up in CL enabled too. So just check out the documentation on that. But yeah, this was an interesting one because there's, in the radio astronomy community, there's a library package called XGPU that a lot of them use, but it's not particularly dynamically configurable. Like if you want to change settings, you got to recompile the library. And if you want to set a certain number of antennas, it's great at really, really big numbers of antennas, but there's rules about the number of antennas that can be used and like pipelines and basically there's only certain combinations. Like you couldn't say I want 5 because that may not work, right? It wouldn't compile. So one of the things we wanted to do with this X engine was to be incredibly flexible. We wanted to handle everything from like 2 to 42 antennas. So there were no limits in terms of how you could configure the pods for the antennas. It's still in OpenCL. There are some folks out there that are still using AMDs, right? And you know, one of the things I like about GNU Radio, trying to keep it as flexible as possible, is like, you know, if I lock this in the CUDA kernels, then those folks would be able to use it. So there was already an OpenCL base that was in there. And with that in mind, then you don't have to do recompiles and all that stuff like you have to do with XGBU. So you could just change some parameters in your flow graph and rock on from there. So there were a couple of systemic challenges, and back in the spring, on the scheduler calls that Josh was talking about, Josh and Bastion and those guys, they went through a much longer. I think we were trying to keep it to under an hour, and we ended up talking for about an hour and a half. So they've seen some of this stuff, and I think that they've got that in mind with the scheduler in terms of some of the performance issues we ran into and how we ended up fixing it. But systemically, one of the things that I ran into at really, really high speeds was the GNU Radio work function. Like if you return 0 because you're not ready to process any data yet, it took forever forever in the terms of microseconds for the scheduler to call that work function again. And so once I figured that out, I had to do some other things within that work function to kind of hold to get around some of the schedule limitations. But NUMA, and I know there's been talks at past GRCons about this, but it really, really was important on these multi-CPU systems. The way that they're allocated, it almost looks like 2 computers that are kind of connected through these interconnects. And if you cross these interconnects, it is much slower. So if you don't take that into account when you're doing some of these things, like some of the memory allocation in the thread starts had to actually happen in the start function, because if I did it in the constructor, when the GNU Radio flow graph started up, that particular thread that was starting all that was on a particular CPU and core, but that wasn't really where I wanted things. I wanted it to actually be where it got allocated at start, so it would actually spread it out correctly. So there were some tricks that we had to tackle with that. The other one, the last one that was a little bit interesting, and I think this drove a lot of some of the challenge and performance with the networking and synchronization blocks, was this, that if you just look at the F functions and you just look at the X functions, and the paper said, well, this is better to separate these two, as soon as you stick a network in the middle, you're introducing some other problems. So TCP is definitely not the way to go with this. UDP is definitely better because you don't have all the retransmits and all that stuff to worry about, which are great, but it'll slow this down. But that means you got to worry about things like jitter and queuing and what happens because you're inevitably going to miss packets. And if time and synchronization is really, really important, and like you're looking at 12 antennas and 2 of them are dropping packets and the other aren't, like you got to handle all that in code and you got to do it in real time. So that introduced some other things that weren't insignificant in the final design. So this is a little busy. I don't know if you guys can read this in the back, because I was noticing when I was sitting back there, some of the smaller fonts were a little bit hard to read. But yeah, some of the challenges that I ran into at each step, and again, this was some of the stuff that I talked about with the scheduling guys, but the snap block, the number one thing I had to worry about was packet loss. And that drove a couple of things. Keeping up with the data streams at the rate that they were coming in was a challenge. I went through a couple of iterations around, can I do all this in one thread? Can I do it in the work function? And it was just too slow. So I had to spin out another thread. And so now you've got 2 threads per block. And I talked with some other folks that were doing really high-speed network comms for signal processing, but their scenarios were a little bit different. Like they were just pulling data from one radio. They didn't have a number of different sources feeding. So that was definitely an issue. But there's some other interesting new things that came up that I'll talk about in the solution side. That if folks are working with high speed, there's some nice easy fixes you can pull in. The synchronizer block. So version 1, I was doing some queuing on there and trying to stack the data and to make up for like if you missed blocks coming in. And that was just horrible. So that got pushed back into the network block. Version 2 and 3, like I tried to do some more things with general work. And basically the whole thing was you had all these multiple things coming in at different orders and you want to kind of get them to stabilize. And as long as the network blocks are filling in the missed gaps, they should stay that way once they get there, right? And that helped a lot. But what ended up happening was that block turned into a single threaded work function that was just doing a whole bunch of mem copies. And it eventually just kind of maxed out. Like I couldn't get more than about 5 antennas to work when that block was in there, which is why I kind of moved the functionality around a little bit. But we already talked a little bit about the X engine and XGPU and being able to do some of this stuff in real time. For folks that are interested in the GPU stuff, I'm going to talk a little bit about some of the GPU challenges that I think will help with some of the scheduling as we're looking at getting GPU capability and heterogeneous computing in there. But there were some interesting challenges that came up in there. The other thing that happened too is the way that the Snap board sends blocks of data out. It was sending out, each packet has 16 like sort of vectors. Each one's like a time sample. And what I found was if you just let GNU Radio kind of do its thing and the output multiple varied, it had a huge impact on performance. So if I locked that in to match what it was getting on the far side, like you could see the back pressure start to build, like it wasn't keeping up, and then memory would get really high, and then it would kind of max out, and then suddenly you just start dropping data, and the correlator wasn't keeping up. But matching out that output multiple with what was coming in on the inside actually helped stabilize that quite a bit. And then doing high-speed data to disk, when it goes to the correlator, it does decimate quite a bit. So the output data for each frame is really, really small. So we're integrating on the order of like 20,000 frames. So the data reduction is pretty good. But getting that data to disk and doing it quickly was super, super important. Like a traditional like SSD is sort of okay. And you're probably looking in the like 500 megabytes a second kind of throughput to disk, but even that could back stuff up a little bit if the disk isn't keeping up. So like NVMe's at like 3,500 megabytes a second was really where we needed to be. So the boxes actually have these large NVMe disks in them to store data in real time. So how do we fix some of this stuff? This is like the good stuff for the scheduler guys, right? So the work function, I ended up putting some sleeps in there so it just wouldn't exit until it needed to. And I was talking with Josh and the guys about that a little bit. But it'd be really cool if we could have some control over the scheduler to say, like, you know, if we don't return anything, like how fast do you want me to let you know like something else is going on? So that kind of thing would be really helpful. So the other thing I ended up doing was getting feedback from the synchronizer. So as the data comes out of the Snap source block, it tags it. So it's got all the timestamps in there. But that whole tagging function was actually kind of expensive. So like dealing with STD vectors and tags was great and it was really flexible, but there was a really big performance cost for it. So what we ended up doing was the X engine actually will come back and notify, hey, I'm synchronized now. Don't worry about tags anymore, and it'll kick that stuff out. There's also some of the PMT message blocks out the other side. And like everything mattered. I felt like, you know, you're kind of ripping out all these components as much as you can to get as much performance out of things as you can. And I didn't realize this early on, but like if you look at how GNU Radio looks at topology of blocks, it may know when like the standard inputs and outputs are connected, but there was no way to know if like a PMT message port actually had a connection to it or not. So we had to add a flag to that because if you just produced the PMTs, it was again just another piece that slowed things down a little bit. There's some newer things on the network side of things too, this multi-message receive capability where rather than just grabbing a packet at a time, you can actually set it up so that you can take blocks of packets at a time. So it just becomes much more efficient to say, like, don't give me one packet and then do something with it. Give me another one. Like, give me 16 of them. I'll deal with them all at one time. And that was definitely more efficient. We got a nice performance boost out of that. And for folks that have the Mellanox network cards, there's this libVMA. And again, I didn't know about this early on, but you can just LD preload this libVMA, and it kind of does what DPDK does. Like it bypasses the kernel buffers and just takes the data from the network card straight to user space. So it saves some mem copies and moving the data up the stack. And that helped out quite a bit as well. Let's see what else we got there. Oh, yeah. So, in GNU Radio, I feel like I'm always so used to working with like 32-bit floats. And yeah, 8-bit floats out of there seem to be fine. But as I was looking at performance on the correlator, some of the GPU slides, you'll see some of this too. But there's kind of two pieces to GPU optimization. Well, two major ones that come up at first. First is moving data to the card. So if you gotta move a block of data to the card, it just takes some time because you're going off host and onto GPU. And that's a big piece of it. And then the other piece is the kernel execution time, right? And so there's kind of this optimization curve. Like if you only transfer a little bit of data, you don't get the full throughput to the card that you could. So you got to actually, the bigger the block of data, the more gigabits per second will actually transfer to the card. But on the flip side of that too, if I got to send 32-bit floats, it's still a lot of data. So what we ended up doing was keeping the 4-bit packed and just moving that, and then doing all the unpacking on the GPU, and that actually had a significant CPU performance input. There's also some other things you can do with like GPU memory pinning, and that's something that's in the API calls where you can lock it in on the driver. That just doing that without changing any other code was like a 2x performance increase on getting stuff to the GPU. The other thing that you really kind of almost have to design to the GPU architecture. It was like, this was always what would happen. So I'd be working on something and I knew I needed more performance, and then I have absolutely no idea how to do it. My brain would chew on it for a day or so, and then suddenly something would hit, right? But like optimizing the newer cards, like the 2000 series cards and the 3000 series cards, their memory access to move data to global memory actually happens in like 256-bit or 384-bit chunks, right? And so if you try to read floats and it's kind of doing these smaller ones, it's not really efficient. So just optimizing some, OpenCL has this, they call it float 4 and float 8 data types. And so basically doing that aligns the memory reads for, say, a number of IQ samples. But if you just did them one at a time, it was like one memory clock cycle, and it'd be a bunch. If you did it as one of these, it would read a number of them all at one time. So it was another big performance increase we got out the other side. The other thing that was a little bit interesting was I don't know if you guys can see it or not, but the data that comes down has this, like, time is one of the matrix parameters. It's frequency, it's the station, or basically antenna, and then the polarization, right? And if you don't get that order right when it gets to the GPU memory, it's just not as efficient. That actually turned out to be quite a problem. So there's another kernel that I run in there that kind of reorders it, and just reordering it before I did the correlation was another like 2 to 4x speed up on the throughput side. So into the GPU side, it's interesting that typically with the GPU side, you'll see, like, is this a memory constrained problem or is this a compute constrained problem? And generally what they mean is, like, is the total time it takes to run something based on how much it takes to move the data to the GPU and back, or is it what's actually being processed, right? And so the cross correlator actually turned out to be like a memory compute constrained problem at really, really low antenna counts. So if you're under a dozen or so, the time it takes to move the data to the card is way more than it takes for the kernel to actually do the cross correlation piece. But as the number of antennas starts to increase, then obviously the compute starts to go up, and eventually they kind of find a balance, and then at some point the compute actually starts to get higher. And so the way that the math works on the cross correlation is that it grows with it's an n times n plus 1 over 2 kind of thing. So it's like an n squared order of magnitude. So as you add more antennas, it grows pretty quickly. And so, like, in that middle range, like 17 to 23 antennas, there's a little bit of a balance, but the kernel cost was definitely going up. And then on the high side, global memory access actually kind of dominated the performance drop off. And you can kind of see, I was talking about some of the speed ups that we got, like reordering the matrix and moving to the 256-bit optimized, like float 4s and float 8s. The worst curve across the top was kind of where I started. The yellow curve was where XGPU was using float inputs, and they can actually do 4-bit now, but this was where I started with that, was the 32-bit floats. The red horizontal line is my real-time layer. If I'm not under that, then I can't process this data in real time, and so that was my metric to try to move things down. And you can see how reordering the matrix like really jumped it down, because it was starting to take advantage of things like the cache hits and stuff on the GPU to optimize it. And then, I ended up going from, say, 2021 antennas to 23 antennas just by going to the float 8. And it looks linear, but when you look at it, and again, think about the n squared, that was actually, going from 21 to 23 antennas on that curve was actually a pretty nice jump. So this is, for folks that do GPU work or care about GPU work, this is where it kind of gets interesting, right? So if I take each of those pieces, as we're trying to optimize this correlation kernel, and break it down into its individual pieces to look at how the timing goes. So this is like the 42 antenna case. This is like the worst case that we'd have at the ATA, right? And so the first purple one is the amount of time it takes to move the data to the GPU. And the red one that's kind of there next to it is the amount of time it takes to unpack the 4-bit and then reorder the matrix. And then that big yellow piece is how long it took the kernel to run. And it doesn't even show up, but there is one more to the right, which is the amount of time it took to move the output data back. But it's, again, since it's stacked so much, there's not really a whole lot of data to move back. It doesn't even show up when you're looking at it in terms of the individual kernels. And this is interesting, right? Because this is like, all right, well, if I want to go faster, this tells me pretty quickly like where I'm going to get my most bang for the buck to focus. And this looks like a compute problem. And if you start to say, all right, well, I'll go from a 2080 card to a 3090 card, it should be twice as fast, like this is going to get better. Or like, what if I start using some new tensor cores, or what does this look like? But I wasn't convinced that that was really what the problem was, because the math is super simple. Like it was just it was a couple multiplies and adds, and it just does it a lot, right? So the math wasn't really hard. And so what I ended up doing to figure out where the real problem was GPUs have this concept of what they call coalesced memory. So think of it like, C of I equals A of I plus B of I, right? Where you're always accessing memory locations that are kind of in the same piece, right? And so that's like the most efficient way to do math on the GPUs. It takes advantage of all the cache optimizations and all that kind of stuff. And so I said, well, I'm not going to care about the results. Let me just see what's really going on here. I'm going to use coalesced memory access within the multiplies and adds, just for the sake of argument, and see what happens. And what it ended up falling out of that was that the actual compute time was for the math was only around 6 milliseconds. Like it was super small. The rest of it was the fact that the way you've got to do the integration and look at the different timestamps for different antennas, you ultimately have to keep striding through memory. And so as the number of antennas went up and the number of frequencies went up and your time integration went up, the data points that you needed to hit across all of the antennas in there started to get spaced out further and further in memory. And what's happening was it was missing on cache hits. So this actually wasn't a compute problem. It's a GPU memory cache optimization problem. So that was actually good, because it kind of told me if I spend too much time trying to figure out how to do the math better, like I'm optimizing a 6 millisecond problem, not a 390 millisecond problem. Which kind of drives to, this kind of stuff's never done, right? And obviously, we're doing this kind of nights and weekends. There's still some more work to do. I think on the GPU side, the last two things I really want to hit in the code is that I think there's an optimization function to hit that's based on the number of stations, the number of frequencies, and the architecture of the GPU card. And what I think will help with that really tall, the one that takes the most time on those 42 antenna cases, is to do something ahead of time when we go to start up, to hit a couple of the different metrics and try to figure out what that curve looks like, and optimize the integration time such that for any block of data, the stride is optimized as best we can. And I think we can get a couple more performance increases out of that. The last piece that I didn't do when I started, and I probably should have, but you don't think about it as you're trying to take the CPU math and move it into the GPU, was to do some overlapping memory and compute. So on a GPU, the GPU can actually run kernels and do math while the memory's moving data in and out. So it does give you the opportunity to do those in an overlapping fashion. And if they're relatively close in time, yeah, you can just clock time start to finish. If they're sequential versus overlapped, you can get some processing time back. So we got to go back and do that. There's been some other really interesting things that came out of it. Like there's some new AMD EPYC CPUs that are there. So those are the ones that have the 3090s in it that are trying to take advantage of PCIe 4 because at the time, I guess, when the boxes started coming in, Intel didn't support PCIe 4 yet. But there's some performance things going on the EPYCs that when we didn't see on the Xeons, and we're not exactly sure why. Like thread performance still matters when you're looking at this. There's so many threads out there, and even if you have 48 cores on your CPU, but they run at half the speed, does that mean that you can't keep up with network packets because that is actually running in one thread, right? So there may be some of that kind of stuff going on. There's some places where I think just on the network pieces, if we can reorder the data output on the snaps, it would turn some moving the data around into a mem copy versus a couple of for loops to disentangle the data. And some quick tests showed they probably get another 20% improvement out of the network blocks just by looking at some of the layering on there. Yeah, there's also there's a number of mem copies in there, which I always feel like I hate. But I've tried some other options around using locks or trying to do some zero copy stuff. And it actually turned out some of that actually performed worse. There is a CPU cost for doing locks, and if you're doing a whole lot of them and then you time out the processes, the locks can actually contribute quite a bit to some of that processing overload. And so I think there's some more work to do to look at how to do that a little bit more efficiently. And the multicast support we talked about, but really the big thing is can we get all 42 antennas online? So ultimately, this is what we were working towards. This is the GNU Radio flow graph. If you guys wanted to run it, you could, right? So this was the 5 antenna one because it fit on the slide a little bit better. But these are 5 snap inputs feeding into the correlator block, and you can see the dotted line messages that come out of the X engine that basically will tell the snap blocks, hey, I'm synchronized, just send me data now. And so the top picture was what we got. That's Cassiopeia A. We did 3-hour observation with just 256 channels. The top one was what we got with 5 antennas. The bottom one was when we actually got to 12, and you can see the difference in resolution. But this was what I ultimately wanted, right? I wanted sky pictures. That was cool. And we did ultimately get there. But so the other thing we wanted to do was make this easy and repeatable, right? So it shouldn't have to be me or Whale or Daniel that always runs this. Any of the interns that come to the ATA or any of the scientists that come to the ATA to do observations, or if any of the GNU Radio community wanted to do observations, could we make this super simple? So we took all the flow graphs and basically kind of parameterized out all the stuff that you need to do an observation with the antennas correctly. And actually in the GRATA apps section, these apps are in there, so you could actually just clone that and run it and get some of the observations out. But it turned into be one-liners, right? So we do a calibration observation. So we do 5 minutes on a calibrator and then come off that, and then you go to your sky target, and we do 2 minutes on, 8 minutes sleep, and we run that for maybe a couple hours, go back to the calibrator, come back and run a couple more hours on the target. And then once all that was done, then we could post-process the data and get the sky images out. But we really tried to boil it down to be as simple as that. So you don't even have to create new flow graphs if you want to change the number of antennas or configs. You can do it all from a bash script. Ultimately, I always forget stuff, so I put it in bash script so I can just fire it off and go. There's a lot of good documentation. I felt when I got to the end of that, if I didn't brain dump and write it down, nobody else would be able to reproduce it. So I tried to spend a good bit of time in GRATA and CL Enable to talk about all this process. So the entire process, step by step on how to do that with some of the example commands and everything's all up in the documentation for GRATA. And some of the post-processing, to actually go from running the flow graphs to getting images, Daniel Estevez has another repository that he uses for some of the other work he's doing with the usurps and such that are there, but we just kind of created one bigger one that could do both. So there's links over there to get to Daniel's stuff that helps with all the post-processing stuff. All right, I did it. I know I'm between you guys and lunch, so it's 12:02. So that's it. Any questions?
All right, do we have any questions for Mike? All right, yeah, no, certainly a lot of information there, so I look forward to, digging deeper, coming back to this presentation. And
yeah, so I'll be in the DeepSig booth, so we're out there. If you guys want to catch me one-on-one or chat about anything, feel free to stop by. I'm happy to chat about any of this.
All right, cool. Thanks, Mike.